Très bien. So, hello everyone. My name is Tijan Ishet. I'm from Telecom Sud Paris, and I'm having the pleasure and honor to be heading the Defense Committee today. So I will take just a few seconds to present the other members of the jury. So we have at distance Vivek Borkar from the Indian Institute of Technology at Bombay. We have on my far right Mr. Georges Zakour. He's from HEC Montréal. Mrs. Nidhi Hegde, she's from Bell Labs. Mrs. Clémence Magnin, she's from CNRS Université Pierre et Marie Curie. We have also Pierre-Henri Morand from the University d'Avignon, Eitan Altman, INRIA University d'Avignon, et Yezekael Ael, Université d'Avignon. And so, Alexandre, now you have 45 minutes to tell us a little bit about your works during your thesis.
Okay, first I would like to thank everyone to be here today. And my work will be basically about game theory applied to online social network, and more precisely we will study competition over visibility and popularity in online social network. I would like to thank my thesis member to be here today, and also I would like to thank the European Project Congress that give me some fund for my PhD. So, online social networks. Online social networks are websites where a subscriber can create a public profile, construct relationship with other users, and get more information about this user. Famous online social networks are Facebook, Twitter, Tumblr, and Pinterest. And the reason why we study it is because it's become a really large phenomenon that most of the internet users are engaged. A simple example is about Facebook subscribers. There are now 968 million of active daily users. And online social networks have a lot of impact, economic impact, sociological impact. For instance, I've read, I think, two weeks ago in Liberation, a newspaper in France, that terrorists use online social network to recruit people. And this is why it's really important, I think, to study online social network. And I will go through three main challenges in online social networks. The first one is, how can a company use online social network efficiently? Indeed, companies observe that investment in online social networks increase their sales. And even if they notice that, they really don't understand how it works. They don't know what kind of strategy you can use in order to be popular. And researchers have worked on this question. The perhaps more oldest paper, not exactly online social network, but social network, was made by Campe, Kleinberg, and Tardos about maximizing the spread of influence in a social network. There is also work in machine learning made by Leskovec, and try to find the best headline in a content in order to be popular, and also empirical studies. Okay, this is the first challenge. The second challenge is about the control of misinformation. Indeed, with the online social network, we observe a sort of democratization of the information. It means that everyone can access to information about any event. It is really nice, because usually when you want to have some information, you go open a book, or perhaps, I don't know, use Wikipedia or a newspaper, but now you can just ask your friend in online social network. But even if it's really great, there is a problem because information is not reliable. You don't know if the information posted in online social network is true or false. And there is like kind of two questions. First of all, how to be able to detect a true or false information, and the second question is, assuming that there is a propagation of misinformation, how to control it, how to contain it. And again, you have people that try to formulate this challenge as a mathematical problem and solving using tools from optimization. But also there is some work in machine learning, more precisely natural language processing approach, where they try to detect some pattern in the messages, in the writing style that will tell you whether or not a message is false. The last challenge is about how to solve the privacy dilemma in online social network. Indeed, in online social network, you have a privacy dilemma because if you want to interact with people in online, you need to share some personal information. It's the same in a classical social network, not an online. If I want to interact with you at some point, if I really want that you become my friend, I will share information. But the problem is that in online social network, when you share information, the online social network owner possesses this information and can use it to sell it for a company, perhaps for targeting and so on. This is the reason why there is this privacy dilemma. And there is some paper that use game theory to model this problem, and also some empirical studies that prove that there is really a privacy dilemma in online social network. And in this talk, I will focus myself more about how can a company use an online social network efficiently, and more specifically, I will try to find answers to the following three questions: how to maximize content's popularity, how to model the distribution of messages across sources and topics in online social network, and also how to maximize content diversity. So, because we're interested in the maximization of popularity, what are our agents in an online social network? Our agents are sources. Sources as people who post content. It can be company or perhaps just me. And you have also readers that, read your content, as you can expect. And what is really puzzling in online social network is that you have many strategies. You can post in different places about different topics. You have different channels where to post. And so it's really complicated to find a nice way to model this kind of problem. But what is nice is because you have sources that all try to maximize their own popularity, a game theoretical framework seems to be the best adapted to this framework. So here's the plan for today. Please don't be scared. We have three lines of works here. First of all, the visibility competition. Second of all, the popularity competition, and third of all, the posting behavior dynamics. And in each three line of work, we will have three parts. The first one is observation. We will make empirical observation on data to see how it works online social network, and based on this empirical observation, we will try to make a good model, and then we will analyze this model and try, for example, if it's a game theoretical model, you solve the Nash Equilibrium, compute the properties. So let's go through the first part, visibility competition. We start to study with my advisor visibility competition because when we start to look at the popularity competition, at some point we tackled to a big issue. It was too much complicated. There is too much strategy, too much effect, too much influence, too much parameter, and we don't really know where we start. We had the feeling that we need to go back to the basic. How I can be popular? Okay, at least I need that my messages will be visible on the online social networks, that subscribers will see my messages. This is the reason why we have started this visibility competition. So, in order to understand how to be visible in online social network, it is important to, first of all, understand how people read messages in online social network. And most of the time, they read messages through a newsfeed. A newsfeed is public area where news are published. The people who publish in this newsfeed can be friends, advertisers, companies, and you can have newsfeed can have different names depending on the online social network, such as wall or timeline. And here is an example of a newsfeed. So, our first empirical question, we try to answer the following question: how to be visible on a newsfeed? And here on this graphic, you can observe that in the x-axis, the fraction of popularity gets on the first position on the newsfeed. For example, I have messages and it stay, I don't know, 1 hour in the newsfeed. How much popularity I get when I stay in the newsfeed. And here is, in the y-axis is the number of messages, more precisely the density. We extract this data from Facebook this data is coming from the Facebook page of the mayor of Paris, Anne Hidalgo, and we use a software called NetViz. And it is really interesting to note that more than 70% of the posted contents reach 80% of the total popularity, while the content is in the first position in the newsfeed. It means that if you want to be visible and popular, you need to be always on the top of the newsfeed. It means that you need always to have messages on the top of the newsfeed. So, based on this empirical observation, we will go through now the mathematical model. We consider the following. The instant arrival of messages from a source J about a topic C in a newsfeed is modeled by a stationary ergodic point process, and its intensity is lambda JC, and we assume that the intensity is finite and null for mathematical reasons. And by using PAM probability theory, we prove that when an arrival of messages occur, the probability that the messages coming from source J and about topic C is given by the ratio between intensity. And this is how we define our visibility measure. And we assume that a source J can post different messages about different topics. So his strategy is a vector, and you have C topics, and the source J can control the intensity of the flow of messages sent on each of these topics. And we will assume that the UDT of the source J is the weighted sum of the visibility measures minus a cost for sending messages, because we assume that you cannot, creation of content costs something. And because everyone is trying to maximize its own utility, we will use the concept of Nash Equilibrium to solve this game. And so here our first result. The interior Nash Equilibrium is unique. When I say interior, it means that everyone is sending flow in the newsfeed. There is no flow equal to 0. At the interior Nash Equilibrium, each source sends messages about a unique topic, and this is really interesting because it means that it's suboptimal to send messages about 2 topics for a specific source. You will always try to maximize only 1 topic, otherwise you lose visibility. Moreover, at the interior Nash Equilibrium, the sum of flow is a solution of a concave programming problem. Okay, this property is a mathematical property, but it's an important one because it will help us to prove the uniqueness of the Nash Equilibrium and also help us to design a decentralized algorithm that converge to the Nash Equilibrium. And the last result is that we have a mathematical expression of the Nash Equilibrium, which is written here. And what is interesting to note is that it is decreasing in the cost, of course, means that the more I have to pay to create content, the less I will post. But also, it is interesting to note that it is quadratic concave in the number of players. Means that at the beginning, before threshold, the more there is players, the more I will post messages in the online social network, and then after some threshold, the more there is player, the less I will post. And you can find also this in trends, right? For example, at the beginning, after a threshold, there is a lot of people who adopt a product, and when there is too many people who adopt a product, you stop to adopt it, right? And this is kind of similar behavior. The second part of this line of research is to find a decentralized algorithm that converges to the Nash Equilibrium. In this kind of game, it is an hard question because we are not in a quadratic game or classical game, it's not a linear game. And also, we don't have the usual property to prove the convergence of decentralized learning algorithms. Usually, you need the potential property or perhaps supermodularity property, but here we don't have it. But we were able to still design an algorithm by using two time scale scheme, where at the fast time scale, each sources try to imitate the other sources, means that I watch what do the other, and I will try to imitate the average behavior. And then on the slow time scale, I just try to maximize my own utility, means that I use a gradient scheme to do so. And here is the scheme. We assume continuous time, and so we have differential equations. Okay. And so here it's a numerical illustration of the convergence, and you observe that first the behavior of the sources converge to the same behavior, and then they both maximize the gradient, and so you reach a symmetric Nash equilibrium. This algorithm only works for symmetric layer. Okay, now I will go through the second part of my talk, popularity computation. When you talk to economists or just to I don't know, to friends, and you say, okay, I'm working on an online social network and I try to maximize the popularity, they always say the same thing. Okay, it means that you try to pay the online social network such that you will be popular, right? Indeed, for example, using YouTube or Facebook to get popular, you just have to give them some money and they will do the advertisement for you. And this is why now we are trying to study a popularity competition where each sources have its own content and pays the online social network in order to be popular. So, the first empirical question, the first question that we try to answer is how to model the popularity evolution of the content. And here again, we extract some data from Facebook, from a Facebook page posted again by the mayor of Paris, Anne Hidalgo. And we have the following cumulative curve of popularity. And it is interesting, it's kind of inverse exponential. So when we look at this curve, we see that the following linear differential equation will well approximate this curve. And now let's go through the math. We assume that we have n competing sources, release the content, and we assume a population of potential viewers who can access each of the n contents. And one of the big hypotheses here, assumption, is that the access is exclusive. Viewers do not acquire another content after accessing one, right? It means that, for example, you have two videos of the same music or talking about the same thing, and you will only watch one of them, one of the videos. You are not interested to watch both. And we assume that the content I is accessed by randomly picked viewer every 1 divided lambda seconds. So we, based on the previous assumptions, let xi be the fraction of viewers of the source j, and the evolution of xi described by the following linear system, where you have basically the same equation as before, but you have 1 minus x, where x is the summation over j of aj, and it means that this is coming from the exclusivity hypothesis, means that, remember, you are not interested to see 2 videos, you are only interested to see 1. And ui here is the acceleration control for player I. We say that when you pay the online social network, it will only accelerate your dynamics, okay? And of course, because you pay, you have a cost, and we assume that this cost is linear in this case. About the linear cost, I have taken this assumption because when I have looked to Facebook, for example, my Facebook page, and I look at the cost for sending messages. I've just plotted the curve, and I see it was linear also, so this is the reason why. And we assume infinite horizon means that a source will participate to the content diffusion in some infinite time interval. It's interesting to the wall, means that I'm interesting to be popular at the beginning and also like at the end of time. But of course, because it's not a realistic assumption, we add a discount rate in the sense that, okay, perhaps I'm interested in what happened at the end, but okay, I will focus myself on the beginning, and the discount rate is made for that. Okay, and here's the cost of the source I, and you see that this is a weighting sum between the popularity and the cost for sending messages, for accelerating the content. So you try to be as popular as possible, but you try that it's not cost too much. And the value function is defined as the infimum of this cost function. And here we go, our results. So the first thing is I have to recall what is a bang-bang strategy in optimal control. Bang-bang strategy in optimal controls is a strategy that only take extremal value. Extremal value. Here, you min or Umax. And bang-bang, it's really good because it's easy to implement. Means that assuming that I can invest 10 euros per day, at the maximum 10 euros per day in YouTube, a bang-bang strategy will say, okay, today you invest 10, tomorrow 0, today 10, and so it's just 0 and 10. But if it's not bang-bang, perhaps the optimal policy can be today you invest 10, then tomorrow 5, perhaps the day after 7. So I think it's really nice if we're able to get this kind of strategy, and of course we get, this is why I talk about it. We know that, we prove that the value function can be attained by a strategy you have of bang-bang type, and our other result is the following. In the symmetric game, means that where all the parameters are equal for everyone, and if you have incentive for sending content, for invest in the content, then the symmetric Nash Equilibrium is a threshold type strategy where at the beginning you invest as much as possible, and then after the threshold you start to invest. And here's the expression of the mathematical expression of the threshold, which is okay here. And this is interesting also. This is interesting to note that this threshold is decreasing in all the parameters. The more there is player, the less I will invest. The more my content have a potential popularity, lambda, the less I will invest. Okay. And now I will go through the third part of my talk, the posting behavior dynamics. It's related to the first part in the following sense. In the third part, we define a model where sources try to maximize their visibility by sending messages. But it's a static game. Even if we find a decentralized game, a decentralized scheme that converges to the symmetric equilibrium, we are not exactly sure that it will be the real behavior of people who post. And here we will try by using stochastic approximation to model how people post messages in online social network in a dynamic way. Moreover, once we succeed to model and find some result about this posting behavior, we will we'll try to control it, right? In the sense that, okay, now I know how sources send messages, how I can control it such that sources do what I want. For example, in our case, I will try to maximize diversity. But first, let's try to understand really how works the posting behavior. And I have AP or AFP who create news, create content, and newspaper company receives these contents. And we decide to post or not in their newspaper, and also in their, or perhaps in their Facebook page, Twitter, according to the following decision. Do I think that the messages will be popular? Do I think this message will be new or not enough? And this is basically the staff of the job of an editorial staff in a newspaper company. And so this is why we came, but to the conclusion that posting behavior works as such that, not works as follows. And yeah, now we're interested to see whether or not our assumption is good, and we extract some data from two Facebook pages, Le Monde and Liberation. We extract the messages, the content, the timestamp, and the popularity associated to each messages. And in the first graph, in the first graphic, in the x-axis, you have the average popularity of messages per day, and in the y-axis you have the number of messages posted the day after. And we observe the following: the more I'm popular today, the more I will post tomorrow. So there is, the popularity is can drive the decision, at least for newspaper company, for posting. And you have also the same, you have also a really interesting fact, is that there is influence between sources. In the following sense, the more I post today, perhaps the less the other newspaper will be popular, or will be more popular. In this case, you have the more Le Monde posts messages, the more the Liberation will be popular tomorrow. So, our two main objectives is to create a model that capture popularity as the main driver of posting behavior, and also models that have influence between sources about popularity. Here it's a generalized version of the posting behavior dynamics, and then we will try to be more specific, but of course there is no way to generalize it. We assume that at each time Tn, only one source C receives the content at time Tn, and this source will decide to post whether or not its content is greater, it's more popular than a certain threshold. It's like, for example, I receive a message, and I know that if I think that these messages will have more than, I don't know, 10 likes or 10 shares, then I will post. Otherwise, I will not post. Here's an example. Assuming that Le Monde receive messages, and you look at these messages and say, okay, these messages will be not popular, so I will not post it. Then the day after, you have Liberation that receives a message again, and you look at it and say, oh, this is looking really interesting, so I will post it. And so on and so forth. Now let's go through the mathematical model. Let Tn the arrival instant of the nth messages in the online social network. Its messages is associated with a kind of mark, means that its messages is associated with a particular source, and for it shows the arrival process of its content from the content creator is an independent Poisson point process of intensity lambda c. And again, we are able to have the probability that when the nth messages arrive, the probability that it's coming from C is given by the ratio between the intensity. Moreover, we denote by YC the total number of messages passed from C in the online social network during 0 Tn, and XC of n the average number of messages posted by C. Moreover, we denote by ZCN the expected popularity of the nth messages from source C, and delta C is the threshold associated to source C. And a source will post if he has the messages, and if he thinks that the popularity of his messages will be greater than this threshold. We also have positive influence matrix A plus and a negative influence matrix which model influences between sources. And so here is the main assumption of the model. the probability that ZC of n means that probability that the alien message is coming from C is greater than the threshold, means that it will pass the messages, is a linear combination of the average of everyone and the weight are the weight was positive influence are respectively the matrix A and then the matrix A minus 1. And so our goal here is to understand the evolution of xc of n. It is interesting, xc of n is a stochastic approximation. We just have to write it down and you will see. And basically it is xcn plus 1 is equal to the previous xcn plus a stochastic term which capture whether or not a source will pass the messages. And here, so the variables that captures the decision of posting from the sources is zeta c, and it is equal to 1, means that the source will pass messages if he receives the content, if the content creator sends messages, and if he thinks that this content will be passed. And a good idea of what is a good decision or not, what is a good, I don't know, law, if this law is good or not. And perhaps the best thing is to see the opinion of everyone such that I will have a good one. At least I will know everything and I can make my decision after that. You have also the same in health information because nowadays with all the health information on the web, assuming that I have like some flu and I just Google it, okay, I have some flu, I have that, and the web or the online social network will say to you, okay, you will die in 2 days. And of course it's false. So there is here also a lot of room for that of improvement, and diversity is a good thing in this case also, because most of the time you are not able to detect whether the news is true or false. Just show all the news and I will make myself, I will make my opinion about it. And again, you have the same for containment of misinformation. So how we do it? We propose to use content active filtering. Indeed, because of the huge number of messages that people receive in online social networks, you have to. The online social network owner have to make some filtering about the information, right? And for example, Facebook proposed basic filtering and strict filtering, and I think there is a new one when they just really try to recommend you the best news, the one that they think the best. And here you can imagine after at the end of my presentation, you can imagine a new button with diversity filtering. So what is diversity for us? When you talk to an economist or perhaps a guy from information theory, the guy will say, okay, for me diversity is Gini index, like inequality index, or perhaps the entropy, the Shannon entropy. And there is a huge number of diversity measures, but in my case I will try to focus myself on one property that all these measures have, the equality property, right? We know that for the Shannon entropy is maximized when the distribution is uniform here. And here we will assume that, in our case, the vector x is diverse if it shows the same number of messages at the equilibrium of the posting bin. And so what is our control? Our control works as follows. It's related to accept or not the messages in a queue in the communication. And here it works as follows. You have a new arrival of content and the online social network owner will decide whether or not it will accept the messages according to a probability PC, which is related to the source of the content. And so our goal is to find P, the vector P, such that the diversity property is satisfied. And okay, here is the closed form of the diverse control. And it works as follows. We have to think a little bit. Why? Who is the guy who passes the less messages? The guy with, according to my model, the guy who will be the less popular. So this guy, we don't do anything to him. It's C prime here. And the other, we just try that they send the same number of messages as this guy. And this is the expression here as PC. And here it's an illustration of our control, and we see that the dynamic of costing behavior will converge to the same number of messages for each sources, and the CAF policy is given here. For the first sources, we will do nothing. We will accept all the messages. For the second sources, we accept only half of the messages, and for the third sources, we will accept 16% of its messages. And now, this is the end of the presentation of my works, and I will just go through a little bit of extension, future direction. I think one of the most important future direction is about welfare in online social networks. I've just checked a little bit online, and when you look at the American Customer Satisfaction Index, online social networks are among the worst performing companies. It means that people, not even owner of online social networks, didn't have really understand what are the needs of the subscribers. What is good with my work is that I'm pretty sure I understand the need of sources, the people who post. Now, what we can do is to take these models and to add the utility of readers. So they are interested in what? In reading good contents, perhaps to be surprised and so on. And if we are able to do so, and compute, for example, the Nash Equilibrium, but we are not obliged to use game theory, we can define new measure of readers and sources satisfaction. For example, I don't know, like related to fairness, similar to fairness measure in telecommunication. And we can also study classical paradox in online social networks, because usually, game theory, because everyone is trying to maximize its own utility, it creates a lot of paradox. Okay, the second direction is about information release in online social networks. Online social networks frequently ask for rich information of subscriber identity, right? But the subscribers are not obliged to provide this information, and can even fake this information to the online social network. And there is a big question about detection of fake identity, and I'm pretty sure that game theory can teach us a lot. The first thing, if we want to have a game theoretical approach, is to understand the benefit for releasing a certain amount of true information for a subscriber. Why I will tell you the truth. Basically, we need to find and understand to the following answer. Why I will tell you the truth? Because if I lie and people discover that I lie, it will be really disappointing for them. And why I will not tell the truth? Okay, because my friend, for example, problem of social class. My friends are really rich, and okay, in order to stay friends with him, then I need to, I don't know, buy a really nice car and perhaps live in a really small flat, and in order to lie to them about my social class condition. And I think, yeah, game theory can be used to model that. And the last future direction is about centrality and opinion maximization. The third part of my work was about posting behavior, and this model can be seen as a model that captures opinion propagation. We already find a way to control it, but really simple ways, the diversity, but perhaps assuming that I have a function that I try to maximize, how can I do optimal control on these dynamics? And because you will apply control to specific node, right, specific source, it will define a kind of new centrality, assuming that, for example, I want to maximize the number of posting messages in the online social network, to which not I have to give money such that they will invest in this online social network and so on. So I think it's defining new centrality measures, and it's interesting because it's based on real scenario context, and usually the centrality measures are more mathematical measures that are really based on real scenario. And also there is a big question about how to estimate the influence matrices A plus and A minus, right? Because most of the time, I just say we have a matrix A plus and matrix A minus that captures influence, but you have the same question about social network. It's not because I know your friends that I know the people that really have influence on you. And how can we solve these questions? Okay. And just to finish, I will just talk during 1 minute about my works. Of course, I work on competition over popularity. It was the main topic of my PhD, but I also work in internet economics, try to solve neutrality issue by using game theory. And I have made also some online social network data analysis, more in computer science, but also I've worked with some political scientists about the visualization of about the visualization strategy on Facebook, about politics, and there is also some work about epidemic control, and that's the end of my talk.
Thank you very much, Alexandre. That was really perfect timing. 43 minutes.
Allez, voilà. On vous attendait. Très bien. Voilà, donc Alexandre, donc le jury a délibéré. Donc on a trouvé que tu as fait une très bonne présentation, très pédagogique, claire et accessible donc, à un auditoire pluridisciplinaire. On a vu que tu as bien su mettre en valeur tes travaux et tes contributions en faisant un choix pertinent sur les différents aspects que tu as choisi d'exposer. Donc, par rapport aux réponses aux questions, donc déjà les questions étaient vraiment nombreuses et on a trouvé que tu as bien répondu à ces questions-là avec aisance et que tu as fait preuve d'une très bonne maîtrise du domaine, mais aussi de l'état de l'art. Donc, le jury estime que le travail contenu dans cette thèse est vraiment pionnier en ce qui concerne le domaine de la théorie des jeux appliqués aux réseaux sociaux en ligne. Donc on a particulièrement apprécié le travail empirique qui accompagne les modèles théoriques et on a également apprécié des outils donc, algorithmiques que tu as su développer dans le cadre de ta thèse. On voudrait souligner le fait que les travaux ont donné lieu donc, à diverses collaborations pluridisciplinaires elles aussi, des sciences politiques, des sciences sociales, etc. Et qu'ils ont un impact potentiel non seulement dans le domaine académique, mais aussi industriel. Donc, pour toutes ces raisons, Alexandre, le jury te décerne le grade de docteur en informatique de l'Université d'Avignon, des pays de Vaucluse, avec la mention très honorable. Et nos félicitations au bac.
Merci beaucoup. J'imagine que vous n'allez pas pouvoir prendre le pont, ça va être un peu short pour certains d'entre vous, donc je veux vraiment vous remercier énormément, vous êtes tous déplacés, pour certains en plus vous n'étiez pas spécialement en théorie des jeux, et pas exactement du domaine, donc je sais ce que ça fait. Je voudrais aussi remercier mes rapporteurs, donc Georges Jacob qui a fait un travail formidable d'avoir lu ma thèse et d'être aussi venu juste pendant 3 jours pour soutenir ma thèse du Canada, c'est impressionnant. Olivier Gorka qui n'est pas là et qui a lu toutes mes preuves mathématiques de ma thèse, un commentaire sur chaque point. Je n'ai jamais vu ça de ma vie. Et c'est grâce à ça j'ai pu corriger tout le manuscrit, voir là où il y avait des améliorations pour les futures publications. Merci à vous. Et pour ceux qui peuvent, je vous rejoins au cours.